So children, now we are starting with chapter number 1, relations and functions. So when I come to the synopsis of this, or say the theory of this chapter, I shall be telling in a very broad sense so that you understand everything and will not be coming back to the theory once again. This is very theoretical, so don't allow your thoughts to go here and there. Continuously be with me. See, from sets we come to, from sets we get Cartesian product. Okay, none of all these you have learnt in last year. From sets you get Cartesian product. From Cartesian product we get relation, and from relation we get function, and from function we get composite functions. Now these function and composite functions, they may have their inverse. Composite function also may have their inverses. Composite functions we write it as like this: F circle G or G circle F, and they may have their inverse also. Now, this is the flow that you have. You have already learned sets, Cartesian product, relations, little bit of relations and little bit of functions you have learned. What is a function in mathematics? Anything and everything which is expressed in terms of the variables and the constants together is called as a function. That function may have any kind of parameter. If the variables that we are using inside the expression is x, we call it as f of x. On one side you have y, and the other side you have 3x square minus 2x plus 1. We call this as our function of x, or maybe x is a function of y, but the standard equations what we express always in mathematics, the standard one is always y is equal to f of x. And in case if this y is having some theta, say 3 cosecant theta plus 2 power theta, something like this, then we call this as f of theta. We don't say f of x, we say f of theta. So here theta, x is a variable, theta, t, anything I use, they are said to be the different kinds of variables, and whatever variables are there, we tell function is of that variable or that parameter. And there can be pairs of equation where x and y also come together. They are said to be parametric pair of equations. So we are coming to functions, and you know this, when the functions are defined in mathematics, they may have their inverse or sometimes they will not have their inverse. What are all the conditions? What is the function? How many types of functions are there? And then in the under these functions, when one function is inside another function, is said to be the composite function. Will they have their inverses? What are the conditions? That's what we are going to learn. And whenever I take any two functions, and what is the operation, any two numbers, when we define certain operation between them, there are four kinds of operations in mathematics: addition, subtraction, multiplication and division. Now these operations, again one inside the other, can be operated, and that is called as a binary operation. So we have something called as, inside this function, after this we have something called as binary operation also. It is of course independent than functions. So this binary operations is defined on any kinds of numbers. We have natural numbers, whole numbers and so on, is it not? So these are all the concepts that we are going to complete in this chapter. Now while coming back to sets, relations, and a little recap of the PUC, first PUC portion, and we'll be getting into the second PUC portion. Even before that, I'll tell you something about numbers. I know you know, but still, just finish with me. You know, we have natural numbers. What are these natural numbers? Natural numbers will be starting from 1, 2, 3, and it goes to infinity. Infinite set we call it as. And natural numbers will be inside whole numbers. So what is the extra element that the whole numbers have other than natural numbers? It has the number 0. So 0, 1, 2, 3, dot, dot, dot. This is the whole numbers. So we say natural numbers is subset of whole numbers. And then whole numbers will be inside integers. Integers. What are integers? Integers are our plus and minus numbers. 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on. So we clearly see that the whole numbers are inside integers. So we say whole numbers is subset of integers. Then we have these integers will be inside rational numbers. Rational numbers is denoted by Q. So what are these rational numbers? Any number which is in the form of P by Q are said to be the rational numbers. So how do I write 0 plus or minus, 1 by 2 plus or minus, 1 by 3 and so on. Again, do you see that all the integers can be written as rational numbers? See, 2 can be written as 2 by 1. So it can be written in the form of P by Q. So we say integers is subset of rational numbers. Now other than rational numbers, there is another set which are called as irrational numbers. They are all non-terminating, group of non-terminating decimals. So I'll call that as Q dash. So what are Q dash? Q dash are all irrational numbers. Irrational numbers. Now this Q and Q dash all together form our real numbers. Okay, so Q as well as Q dash. So what are inside what? When I say integers, it will include whole numbers and natural numbers. You should know about these things. So it was just a recall for you to know about. And other than this, you have something called as what? Complex numbers. Complex numbers is given by the set C. There, each number is in the form of A plus IB, where AB belongs to the real numbers and I is equal to root of minus 1. This is called as complex numbers. Basically, numbers are divided into two parts, natural numbers and imaginary numbers. Imaginary numbers are the numbers which are having I along with them, where I value is root of minus 1. And when you club these real numbers and imaginary numbers together, we get what? Complex numbers, and every complex number is of the form A plus IB. Now, I just mentioned it because it will come inside the functions chapter. Now, I am getting into our chapter. Now suppose I consider the set A is equal to 1, 2, 3. Set A is equal to 1, 2, 3. I shall write the Cartesian product on this set A. Say A cross A. A cross A is given by 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Now this is the Cartesian product A cross A. Now, in A cross A, this Cartesian product, how many elements are there in A? 3 are there. N of A is equal to 3. And how many elements are there in A cross A? You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, how many elements? How did you get this 9? How to get this 9 as such? So, number of elements in A cross A is what? Number of elements in A cross A is n of A into n of A. That is 3 into 3, which is equal to 9. So suppose you have A is equal to 1, 2 and B is equal to 1, 2, 3 or A, B, C. Then if I'll say if n of A is equal to M and n of B is equal to P, then how many elements are there in A cross B? Then A cross B, n of A cross B will be equal to MP, M into P. That's how we have taken here. We have considering only one set, and the same set taking A cross A, we have got 3 into 3, which is equal to 9 elements, and we have written all the elements. Now these are things what you have learnt in first PU. Now I shall go to the types of relations inside this. Relation and types of relations under this. You have learnt relation also. So now I'll make a relation between the x coordinate and the y coordinate to get a relation. That's what is the exact meaning what you see in English. The relation between between two persons, between two numbers. We can build up any kind between two lines, between a curve and a line, any kind of relation as such. It's called as a relation. Okay, how they are linked to each other, how two elements are linked to each other is called as the relation. So now I am going to give you a relation and I want you to pick up the elements from A cross A because I am relating to the set A 1, 2, 3. So I will say R is equal to, say R1 is equal to A comma B. I want you to pick up two elements which in such a way that they should be related under this condition. A is less than or equal to B, where A comma B both belong to the set A. Okay, so I have given you on the set A. Like this I can relate, I can give you anything. A plus B is equal to 3, I can say. I can say B is divisible by A, etc., etc. Now, any kind of relation can be defined. Now that I have defined here, shall we pick out the ordered pairs in A cross A. So I'll say R1 is the list form of R1. This is the set builder form. So I'm going for the list form or the roster form. R1 is equal to, I can take 1 and 1 because 1 is less than or equal to 1. I'll say 1 1. I can also say 1 2 and I can also say 1 3. 1 3. Next I'm taking 2 1. Can I take 2 1? 2 is not less than or equal to 1. I cannot take 2 1. 2 2 I can say because they are equal. 2 2 2 3. Then I can say 3 1. No, I cannot take 3 1 and 3 2 because A is greater than B here. So I'll take 3 3. So see, Cartesian product has any kind of pairing from one set to itself or one set to another set. Cartesian product will have all kinds of pairing, all possible pairings. Out of that, if I am going to choose certain pairs which will satisfy a condition or a rule, then we get what? Relation. So relation is nothing but, you see that all these are picked from A cross A. So relation is the subset of, it is subset of Cartesian product CP. That itself is the definition of a relation. It is the relation between x coordinate and y coordinate of the pairs of the elements of Cartesian product which will follow the condition given. That is the relation. So relation is always the subset of Cartesian product. And now under this relation, there are types of relations. What all relations can we make up? So we'll go to types of relations. I shall keep that A cross A for our reference. I'm going to types of relations. And when I'm coming to types of relation, I want you to remember like this. There are relations called as identity relation, antisymmetric relation. I won't get into such definitions. I'm getting into the definition which is exactly required for us and very important for us. The types of relations is, first one I want you to remember exactly like this. 1, 2, 3. I want you to remember like this. 1, 2, 3 consecutive numbers with consecutive alphabets R, S, T. What does this indicate? R indicates reflexive property or reflexive relation. S indicates symmetric relation and T indicates transitive relation. And why it should be 1, 2, 3? Reflexive relation because we use only one kind of element for reflexive relation. Yes, sir. Symmetric relation, we use two kinds of elements in that A and B. For transitive, I use A, B, C, three kinds of elements. That is why number 3 is transitive relation. So now let us go to the definition of each one of this. You have reflexive relation. What is the definition of this? For all A belonging to the set A comma A should belong to the relation R. And make it a point that for reflexive relation, I need to know what the set is. It is one and only for reflexive relation that we need the set where the relation is defined on. So here on the set A, for every element, or say in the set A, for every element A coming to the relation, you should have A inside the relation. That is the reflection. Reflections should be present. A is the reflection of A. So now what do you mean by that? I'll go back to our example. We have the set A is equal to 1, 2, 3. See, for 1 I should have 1, 1. For 2 I should have 2, 2. For 3 I should have 3, 3. Inside the relation, whichever relation is given to us. I'll take A cross A itself for our example. See, for 1 I have 1, 1. For 2 I have 2, 2. And for 3 I have 3, 3. So I say that this Cartesian product A cross A is a reflexive relation. Now, irrespective of any other elements, any other ordered pairs being inside this relation, my only condition is for it to be reflexive relation for all the elements present inside the corresponding set. You should have the reflections inside this Cartesian product. Then I can tell this Cartesian product itself is a reflexive relation. So, for 1 I have 1, 1, for 2 I have 2, 2, for 3 I have 3, 3. So, this is a reflexive relation. That's the meaning of reflexive relation. Now, I am going to symmetric relation. Okay, for symmetric relation, how many elements am I taking? I am taking two elements for symmetric relation. So now I don't need the set. I only want the relation to check inside the relation itself whether it is symmetric or not. What do you mean by that? For all a comma b belonging to the relation R means already this a comma b is present inside the relation. It is already related in the given definition. Then ulta of this, the vice versa of this, or say b comma a should also be inside the same relation. If you have 1 2, the ulta of that 2 1 also should be present in the relation. If that is so for every ordered pair inside the relation, then only it is called as a symmetric relation. What do you mean by this? The thing is, if there is 1 2 I will have, and for 1 2 I will have 2 1. Okay. If I am having 2 3, I should have 3 2. Okay. If I am having 1 3 and I don't have 3 1, then I say it is not reflexive. Sorry, it is not symmetric. So for symmetric means you go inside the relation, check for every different 2 2 elements that its vice versa also should be present in the same relation. Then only the entire relation is called as a symmetric relation. And now that set is not necessary. The relation will be sufficient for you to find out whether it is symmetric or not. So now I am coming to this A cross A for example. And one more thing is, for symmetric relation or for the transitive relation, you need not take this reflexives for checking, because it will always be true. By default it will be true. So you need not check for 1 1 2 2 3 3. You can leave it aside and check for the other elements. So I am coming to symmetric relation for this A cross A. See, 1 1 I don't want. I'll go for 1 2. For 1 2, ulta of that is 2 1 also should be present. You have 2 1 here. For 1 3, I have 3 1. For 2 1, again I have 1 2. For 2 3, I have 3 2. And for 3 1, I have 1 3. So for all the pairs in the given Cartesian product, you have for every AB, BA also inside the same relation. Therefore, this is said to be symmetric relation. So now I saw that this A cross A is both reflexive as well as symmetric relation. And so for about 100 pairings, for 99 you have the other pair, but for 100th ordered pair you don't have the other pair. Then also we say it is not symmetric. So now I'll come to the third one, which is called as the transitive relation. And since it is the third one, as I told you, we need to have three different elements. So how do you take three different elements? For every two pairs, A, B, and the second pair starting from B, B, C belonging to R, the third pair AC. This implies AC should be in the relation. Okay, now what do you mean by this? AB is true inside the relation, it is satisfying the relation. Then you should start the second pair from this B only. BC, that's also already true, it is satisfying the relation. Then when I say two pairs, the third pair, the corresponding third pair, that is AC, should also be true inside the relation. It should be satisfying the relation, or we say it should be present inside the relation set. Then only we call that relation as what? Transitive relation. Now once again, to check this transitive relation, you need to have only the relation, no need of the set at all. And inside the relation, we have to check for every two different pairs, avoiding the reflections 1 1 2 2 3 3, because by default they are already true. So now I am coming to the A cross A here. I shall keep aside 1 1 2 2 3 3. We don't need it for don't need for checking at all. It is already true. So I am coming to the next pair 1 2. Now 1 2. See, if I am taking AB, I should start from BC, right? So from 1 2, I shall start from 2 only. So 1 2, I'll go to 2. See, you have 2 1. For this, 1 1 is present here. So I'll write what all I'm taking. I have 1 2, 2 1. Correspondingly, this 1 1 is there, belongs to R. Okay. Now I'll go to 1 2 itself, and other than 2 1 anything else, 2 2 I don't want, I'll go to 2 3. So I have 1 2, 2 3. Correspondingly, I should have 1 3. Do you have 1 3? Yes, I have 1 3. 1 3 belonging to R. Now I checked for 1 2. There is no other element starting from 2. I finished checking for 1 2. Next I'll come to 1 3. So now I should start from which element? 3. 1, 3. 3, 1. I should have 1, 1. It is there. So 1, 3, 3, 1 implies 1, 1 belongs to R. It is there. Then 1, 3, 3, 2, 1, 2. 1, 2 is here. So you have 1, 3, 3, 2 implies 1, 2 belongs to R. These are already belonging in R. Okay, I have not written belongs to R. You need to write actually. Then 1, 3, 3, 1 I finished, 3, 2 I finished. 1, 3, 3, 3, 3, 3 I don't need for checking. Okay, I finished checking for 1, 3. Now likewise you should go for 2, 1. Just because you have 2, 1 you have used for 1, 2. There is nothing like there is no possibility for 2, 1. It is there. So I'll go to 2, 1. 2, 1 I should start from what? So I'll write 2, 1 here. 2, 1 I should be starting from 1, 1. 1, 1 I don't need to take. I'll say 1, 2. So I'll say 1, 2. 2, 1, 1, 2. What should you have? You should have the 2, 2. 2, 2 is present here. Is there. So this implies 2, comma 2 belongs to R. Like this, you have to go back and forth and check for every pair. So 2, 1. I finished with 2, 1. There is no other element starting from 1. 2, 2 I need not check. 2, 3 I'll say. 2, 3, 3, 1. 2, 3, 3, 1, 2, 1 I should have. I have 2, 1 here. Again, 2, 3, 3, 2 I should have 2, 2. I have 2, 2 here. I need not check for this. Next, I'll go for 3, 1. 3, 1, 1, 1 I did not. 1, 2. 3, 1, 1, 2. 3, 2 is here. 3, 1, 1, 3. 3, 3 is there. 3, 1, no other element. Next, 3, 2. 3, 2, 2, 1, 3, 1 is here. 3, 2, 2, 3, 3, 3 is here. Okay, we are done. I am done with all the pairings for transitivity from this A cross A relation. So I see that this A cross A is also transitive relation. I hope you understand for transitivity. Now children, if one particular relation is just like our A cross A, if this relation is all reflexive, symmetric and transitive as we see in this case, it is said to be an equivalence relation. So that's one of the most important one you have, equivalence relation. This is all a relation which is all reflexive, symmetric and transitive. If a relation is all reflexive, symmetric and transitive, is said to be on equivalence relation. And the fantastic examples for equivalence relation is A cross A on any set A. I have taken A is equal to 1, 2, 3. Now I have proved for you that it is reflexive also, symmetric also, transitive also. So A cross A is a fantastic example for an equivalence relation. Then E is parallel to on set of straight lines. Let me write. On set of straight lines. This is straight lines. Okay. Or E is congruent to on set of triangles. Okay. Or E similar to on set of triangles. Or is congruent to like this on set of numbers. Now all these are very good examples for being an equivalence relation. You should know. Okay, now let us prove for the first one. E is parallel to on the set of straight lines. How is it an equivalence relation? I have taken one numerical example. I shall take you one statement problem also, where we take E is parallel to as the relation on the set of straight lines. So coming back to recall the types of relations, we have antisymmetric relation, we have identity relation, which I have not told you. I shall tell you in the next class. And now for me, I want all these 4 types of relations to get stuck in your head. It's very important. So reflexive relation, and I told you that for reflexive relation we need the set A. This point is very important. We need the set A to check whether the given relation is reflexive or not. And next, symmetric relation, we see inside the relation itself. For AB, I need to have BA. For transitivity, we use 3 different elements, that is why it is third one. And AB, BC are already true in R. And for AB, BC, you need to have AC belonging in the same relation. Then only it is said to be a transitive relation. Then we have equivalence relation. It is called equivalence relation only if it is all R, S and T, all reflexive, symmetric and transitive. And coming to your PU board examination, equivalence relation generally will be asked for 3 marks. So understand properly that equivalence relation, how to prove for certain statement problems. I am going to give you examples now for equivalence relation. So first of all, I am going to take this E is parallel to on the set of straight lines. Okay, here goes the example. Prove that the relation E is parallel to on the set of straight lines is an equivalence relation. Is an equivalence relation. So we are given, my solution goes like this. I'll call it as L equal to L1, L1, L2 such that L1 is parallel to L2 on L on the set of straight lines. So let me call this as R. R is equal to, this is the definition they have given on the set of straight lines. I have L1. So I'll declare let L1, L2, L3, because I want minimum how many? 3 lines for me to prove all the 3 properties, 3 relations. So let L1, L2, L3 belong to L. And I'll go for the first relation. We'll write the property every time. The first one, reflexive relation. Reflexive relation. I'll write the property for all A belonging to the set A, its reflection A comma A should be belonging to the relation. I want a set of straight lines, and I'll be using only one line, only one element, and I'll repeat the same element in the relation. I'll apply the relation. It should be true. So how do you do when they give you some statement like this? Take only for reflexive relation, take only one line, one element of that set. What is the set comprising of? The set is comprising of straight lines. So I'll take one straight line. I'll call it as L1. For all L1 belonging to the straight line set of straight lines L, L1 comma L1 belongs to L1 comma L1 belonging to the relation L1 is parallel to L1 is true, means a line is always parallel to itself, it cannot be perpendicular. We always say a line is parallel to, we are parallel to ourselves, we cannot be perpendicular to us. Perpendicular to us will be like this, is it not? So L1 is parallel to L1, we are parallel to ourselves. A line can be parallel to itself. L1 is parallel to L1 is true on the relation R. Therefore, and it is true for every L belonging to R. So for all L belonging to L, let me say L here. And now, therefore, R is reflexive. We proved the first property and we'll call it as statement number 1. Now I'll go to the second property, which is symmetric relation. Symmetric relation. For symmetric relation, I should use how many lines? 2 lines, 2 elements. But my elements are nothing but lines from the set of straight lines. So I'll tell like this, I'll put the property. For all AB belonging to the relation R, its ulta BA should also be belonging to the R. So let us say we'll write it orally. For all L1 comma L2 ordered pair, I have taken the ordered pair already, belonging to R. Now what do you mean by this? When I say L1, L2 belonging to R, L1 is already parallel to L2. It is satisfying the condition already. That is why we are taking that. And now I have to interchange the position of A and B, L1 and L2, and see if it is still true or not. If it is true, it is going to be inside the relation. So this implies L2 comma L1. No, this implies that L1 is already parallel to L2. And if L1 is parallel to L2, we know from geometry, This implies L2 is parallel to L1 and this in turn implies L2 L1 belong to the relation R. If I interchange also, by nature, by geometry, we know that L1 is parallel to L2 and vice versa L2 is parallel to L1 is true. Therefore, R is reflexive. Sorry, R is symmetric. R is symmetric. Statement number 2. And now I should go for transitivity. So, I shall take transitivity here. Transitive relation. We'll write the for all A, B ordered pair start from B, B, C belonging to R, A, C belongs to R. Okay, A, C belongs to R. For every two pairs of straight lines, third pair also is there inside I have to prove. So now first of all, how many elements I have to take? Three lines. For that I will take L1, L2, L1, L2, comma, L2, L3 belonging to the relation. I am already taking two consecutive pairs of the relation R, whatever they have defined about parallelism between the straight lines. Now the understood is that L1 is parallel to L2 and L2 is parallel to L3. So L1 is parallel to L2 and L2 is parallel to L3, and again from geometry we know that if 3 L1 is parallel to L2, L2 is parallel to L3, then we see that L1 is parallel to L3 is absolutely true. So this implies that L1 is parallel to L3 belongs to the relation is true, because L1 is parallel to L3 is true on R. This implies R is transitive. R is transitive. This is statement number 3. So 1, 2, 3 implies R is an equivalence relation. Okay, now I have taken a statement like a problem and we have proved that R is an equivalence relation. So there are certain kind of relations where it will be true only for two kinds of relation and not for the third one. First and second will be true, third one may not be possible. So there are so many other examples like that in your first exercise, and we need to prove whether they are equivalence relation or not, or if it is any two of them and not one of them, or is it only one of them and not the other two. We should be able to say. Not only the statement problems, also from the numerical problems. Now this is what is about types of relations, and that are important types of relations. And now let us get into the exercise to start our problems to see whether I will do certain numerical problems of all some 20 to 30 problems whatever you have. I'll do around half of the exercise, the rest half exercise you have to help yourself. And I think once the concept is understood, you can put the concept by yourself.